For this meeting, we will continue our discussion last time on the different anions and cations. But for today, we're going to tackle on the group 3 and group 4 ions. Let's try to take first the boron family, the group 3A. So the boron family composed of the elements that you can see in your right side, or I have my pointer. So these are the elements that could be found in group 3A, and you can see them on their natural state. So in terms of atomic radius, this is how they are being illustrated. So you have there the boron, the aluminum, the gallium, no? And you can see both here the atomic radius and also the ionic radius. And then in terms of physical characteristics, the graph here represents the electronegativity of the different elements found in group 3A, and also likewise the density. Now, let us discuss the reactions of the different elements in group 3A. The elements in group 3A react sluggishly, if at all, with water. So you have here the equation showing the reaction of gallium and the thallium with water. But no, their excuse me, however, their reaction with water is differentiated whether it is just simply hot, that is in liquid form, or it is just simply on a steam. So you can see here the gallium at the aqueous solution, and also likewise forming now only two molecules of hydrogen gas. But when the water is just simply hot, it had produced three molecules of hydrogen. So it has actually the same products. You have the gallium, the hydroxide ion, and the hydrogen gas. But the main difference of their product is that there are more hydrogen when it water is just simply hot, as compared when the water is actually in the steam form. So another reaction, another characteristics of the elements is that when strongly heated in pure water, or pure oxygen rather, all members form oxide. So you have here the general equation, no, showing to you that the addition of oxygen will now form the oxide. All members reduce halogens. So the element plus the halogens, again, this is the common generic equation showing to you the formation of halogen. What is the influence of transition elements in group 3A? Transition elements increases for the larger 3A elements due to poor shielding by the D and F electrons. Hence, the larger 3A elements have smaller atomic radii and larger ionization energies than electronegativities than expected. These properties influence the physical and chemical behavior of these elements. Now let's try to look into the pictures of group 3A elements. Larger group 3A elements exhibit multiple oxidation states. They may lose either the NP electron only, or both the NP and NS electrons. Hence, the lower oxidation state becomes increasingly prominent down the group. Since we know very much that ns electrons form an inert pair. Oxides of the elements in the lower oxidation state are more basic than oxides in the higher oxidation state. This shows to you the electron cloud formula and the structure of aluminum chloride. So compound 3A element has or have more covalent character than similar 2A compounds. Aluminum has the physical property of a metal, but its halides exist as covalent dimers, as illustrated here. No? You have here the elements aluminum, and you have here the chlorides clinging into it, forming or existing as covalent dimers. And as shown also from the electron cloud formula, the dimers are illustrated boldly as being bonded with the dimers using the covalent bond. Okay, what are the boron electrons group are actually trying to exude with? All boron compounds are covalent, and boron forms a variety of network covalent compounds with other elements. And this could be clearly illustrated both in the structural formula and the molecular formula or electron cloud formula. Boron is often electron deficient in compounds, hence it acts effectively with Lewis acid. And then boron forms bridge bonds in which one pair of electron is shared with three atoms. And this could be illustrated also in BF3. This type of bonding is common between uh, not only boron and halides, but also with the element hydrogen. Okay, here is a typical illustration of the covalent bonding in diborane, or wherein boron are actually involved. So you have here the boron and the boron here. So the HB here, the HB in this portion forms the hydride bridge band, or three centers, two electron band. So you have three centers and two electron bands. So if we're going to look at the electron cloud formula, these are the bridge band, this portion here, or it is at this portion, no? And then you have also two electron band, and illustrated here, the normal bands. So another characteristics is that the normal covalent bond formed by overlap sp orbital or hybrid orbital from B with s orbital from hydrogen. So this is the case. So again, in the electron cloud formula, you could see here the sp3, 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 sp3 all throughout from the orbitals of B with s orbitals of hydrogen. So you can see here the band formed by the brown colors, and the hydrogen are formed by the white color. So you have there the unique band produced by the family of boron. And then the boron icosahedron and one of the borings. So you have here boron with 12 electrons. Sorry, 12 elements. And you have here also here boron per se with hydrogen. So you have here the 1, 2, 3, 4, 5, and you have also here the 9 hydrogen, the 3, 6, 9 hydrogen. And these are still under the group of borings. And then we have the beryllium and the aluminum. There are diagonal relationship between beryllium and aluminum. Now we have beryllium and aluminum. There is diagonal relationship between beryllium and aluminum. Both form oxide ions in strong base. So the beryllium will become berylate, and then the aluminum will become aluminate. So you observe from the formula that the oxide ion reacting with beryllium here and the hydroxide ion here. Both have bridge bond. You can still remember our illustration last time in their hydrides and chlorides. So the beryllium and aluminum forms the bridge bonds between OH and halides, not only chlorides but also other halides. Their oxides are coatings that are impervious to water, so they are actually needed in waterproofing. And then they are amphoteric, and they are extremely hard with high melting points. So beryllium and aluminum are usually used in the production of metals. They could be just simply a plating of another metal in order to make them waterproof or to be away from the process of oxidation or rusting. And since they have extremely uh, sensitivity to high melting points, they are very good insulators likewise. And then some aluminum and all beryllium compounds have significant covalent bond. And then we have the carbon family. Again, we will not try to discuss so much about the carbon family because you have already your subject organic chemistry to discuss about carbon. But just simply as a review, the carbon family, not only the carbon family which includes the silicon, the germanium, the tin, the lead, uh, are all part of the carbon family. So that if you're going to look at their atomic radius, the one at the lower portion of the periodic table have a higher atomic radius, and of course it follows with the case of their ionic radius. In terms of electronegativity, it is actually the carbon that has the longest line for electronegativity. And then there's a solid change in the case of the lead. Okay, the scenario of density is very different. You have here the carbon, and then if you're going to look at the others, the dark violet portion uh, goes shorter as it go down to the periodic table. But it is inversely proportional with this, no? The density. The the carbon going down the periodic table has increasing number of density. But in terms of boiling point, it is inversely proportional. So as you go down the periodic table, the boiling point is lower. Now, in terms of melting point, the melting point is proportional to that of the boiling point, except with the case of lead, whereby the melting point is as a higher mark as compared with tin. Okay, in terms of chemical reactions, all group 4A elements are oxidized by halogen. So I repeat, all elements in group A are oxidized by halogens. The plus 2 halides or halogens are more stable for tin and lead. Okay. Okay. The group 4A elements are oxidized by oxygen. Another chemical property to determine probable reaction is that to consider oxides become more basic down the group. Hydrocarbons react with oxygen. Of course, you know that in organic chem. Silica is reduced to form elemental silicon. In terms of bond type and melting process in group 3A to 5A, take note of this table. This is for group 3A, this is for group 4A, and this is for group 5A. Okay, these are the elements. These are the elements also for group 4A, and these are also the elements for group 5A. And then structural formula, bond type, you can see it in the third column. Now let us try to look into the melting point. So you can see here that there is a difference in the gallium. If you're going to look at, they do not have a trend in terms of melting point in group 3A. And then for the case of group 4A, it is actually going down until tin, but not with lead. Much more of the case of the melting point for group 5A. So there's no specific trend for group 5A in terms of melting point. But among the group 3, 4, 5, only group 5A has a negative melting point. That is for nitrogen. Nitrogen is actually the gas that is usually used in order to maintain a low freezing temperature. Okay. Again, let us go back to the bond type. This structure works for covalent network. The covoid structure, metallic bonding. Now, for the two circles, it is covalent bonding. Okay. So, if we're going to look at only group 5A goes for covalent bonding. And then the trend for covalent network, you have here boron. For group 3A, you have the period 2. And then for group 4A, you have silicon and up to carbon, silicon, and germanium. So there is a trend. And then for period 6, all of them follows a metallic bonding. And then we have, of course, the allotropes. The allotropes are different crystalline or molecular form of the same element. Again, then therefore, one allotrope of a particular element is usually more stable than another at a particular temperature and pressure. So, tin, tin exhibits allotropes. The white betatin and the gray betatin. So, as if you have tin and tin bonding together, and also likewise, carbon has also several allotropes, including graphite, diamond, and the lightest object for the meantime, the polyarines. Okay, these are the different phases of carbon. You know that already. Okay, these are the new phases of the elements. You have here what we call as the Buckminster polyarine, and you have here the buckyball. And these are nanotubes, actually, no? This is the buckyball. These are actually small in size. That's why our gadgets are getting smaller and smaller, or more features are being added to our gadgets because you could easily accommodate because of the tubes of because of the shape of nanotubes, or the size of nanotubes are so small, and that the buckyballs also are becoming lighter and lighter. So imagine that this is a nanotube, no? Before, the television of our grandparents has a very big bulk at the back, but now we have what we call flat screen because of the nanotechnology. And then we have tin and lead. We will not discuss any more carbon. I'm sure you are already saturated with carbon. Then you have tin chloride and lead chloride. These are their examples. They are both chlorides, but this is the tin chloride and this is the lead chloride. I am sure what you are thinking now is, what are these for? Oh, that is your assignment. These are actually very oily in nature, but these are both expensive chemicals. These are similar things that I'm sure you have seen already in your organic chemistry. You are familiar with this. This is the freon. The freon is the cooling agent found in air conditions and refrigerators. They are also called as the chlorofluorocarbons. So an example of them is the freon 12. And they are responsible in the thinning of the ozone layer. So If you are an environmentalist, you feel allergic to this structure because this is what we call cooling inside but heating outside. Or sometimes we say also cooling inside but boiling outside. So while we are cooling ourselves inside the inside the air condition, drinking refrigerated water or ice tea, ice soda, but while we are using these air conditioners, while the electric lights are on within our own comfort, the electric fans are open, consuming electricity, burning carbon, while we have the refrigerators cooling our food, the emission of carbon fluorocarbons as well as carbon dioxide is actually heating our own facilities, our own home, our own buildings outside. So we might be moving from one place to another with our air-conditioned cars, but the the freons used for the aircon or the cooling agents, as well as the burning of the gasoline of our vehicles, is actually heating the environment. And let's try to appreciate the silicon chemistry. So the silicon bonds to oxygen to form repeating uh, silicon units are found to be silicates or silicons. So may I read? The silicate building unit is the orthosilicate groupings. Ito yun. No? Which has a tetrahedral arrangement. The silicate minerals are dominant form of matter in the non-living world, especially in the sandy area or in the deserted area. Take note, silicon polymers are synthetic substances. I repeat, silicon polymers are synthetic substances. So silicon per se uh, is useless if they are not formed into polymers. And they have um, a variety of applications or uses that had helped us in modernization or even in the economic development of the world. These are the structures of silicate and ions, and the mirrors are actually the glasses are also um, silicates. The quartz that are used in jewelries, uh, even the glasses of what expensive watches are made up of quartz. And then, of course, nitrogen, phosphorus, arsenic, antimony, bismuth as members of the group 5A. So your periodic table that you are holding right now shows to you where are these things. And they are actually very popularly known to be present in just anywhere of the earth. Of course, you know that nitrogen gas are the cooling gas. Nitrogen is a diatomic gas with a very low boiling point due to weak intermolecular forces. And then phosphorus is commonly existing as the tetrahedral phosphorus molecule. And then yung kanyang dispersal is higher than nitrogen. That is why the combination of NPK, nitrogen, phosphorus, potassium as fertilizer is a very important partnership between the three elements because of their tetrahedra, because of their shape and structure and ability to disperse. Nitrogen has the ability to disperse and link with other elements, much more of the phosphorus. Arsenic. Of course, we do not eat food with arsenic, but the existence are into the physical shape of extended sheets that are covalently bonded together. And then you have also antimony and bismuth. Okay, this is, of course, nitrogen is a gas. And then this is how the solid phosphorus looks like. And also likewise how it looks like when it is dissolved in water. You have here the ore of arsenic, likewise with bismuth. So in terms of electronegativity, it goes down as you go down the periodic table. In terms of density, it goes larger as you go down the periodic table. The same true with the melting point. As you go down, the melting point goes higher, but not with the case of its melting point. Okay, what are the chemical reactions involved? Nitrogen is fixed industrially in the Haber process. So most of the partners of nitrogen in chemical reaction is hydrogen. Hydrides of other group members are formed by reaction in water or acid of metal phosphate and arsenide. Now, halides are formed by the recombination of the different elements in group 5. Okay, these are the allotropes of phosphorus, the white phosphorus, and the red phosphorus. So this is the electron cloud formula of the white phosphorus. So you have the 1, 2, 3, 4, 1, 2, 3, 4. This one is actually this portion, and that if you're going to look at the angle between one phosphorus to the other hydrogen is 60 degrees. But between phosphorus and phosphorus, it is 60 degrees. So 60 and 30 degrees makes the phosphorus strained bands. So ang nag-ipit sa kanila is yung relationship ng band nito at saka yung other pi band of the other carbons. And then we have here the red phosphorus. The main difference is the bond between these two phosphorus. Nitrogen gains 3 electrons to form an ion and 3, but only in compounds with active metals. Okay. The higher elements in the group are metallic and lost electrons to form cations. Remember that always. Oxide changes from acidic to amphoteric to basic as you move down the group. So again, take note of that. From acidic to amphoteric to basic as you go down the periodic table. And then all group 5A elements form gaseous hydrides to form EH3, except for the case of nitrogen. Okay, nitrogens form 6 stable oxides, and these are actually as follows. No? Um, Nitrate is produced by the oxidation of ammonia. It could be converted to two other oxides by heating, and it is a component of nitrogen oxide is a component of photochemical smog. So again, what makes the atmosphere blurred in color, especially in air of urban polluted areas, is actually due to the photochemical smog. It is actually due to the presence of nitrogen and carbon oxides in the atmosphere. And so these are the different elements and compounds of nitrogen. You have here dinitrogen monoxide. The dinitrogen monoxide, of course, you have there the dinitrogen and one oxygen. This is a colorless gas. It is used as a dental anesthetic, but if not used properly, they are called also as laughing gas. And some nitrogen, dinitrogen monoxide are used as propellant and aerosol. And then you have also nitrogen monoxide. So there is a 1:1 ratio now of the nitrogen and oxygen. It is, of course, still a pollutant. And then you have dinitrogen trioxide. So the ratio here is 2 is to 3. 2 nitrogen is to 3 oxygen. And then you have nitrogen dioxide. And then you have dinitrogen tetraoxide. Uh, the 2 nitrogen has 2 oxide uh, individually. The nitrogen dioxide is different from dinitrogen tetraoxide. While the ratio here in nitrogen dioxide is 1 is to 2, and the ratio here also in N2O4 is 1 is to 2, the condition in dinitrogen being a dinitrogen, the nitrogen are also sharing one bond together. So it is a must that there should be 2 nitrogen and that each nitrogen are bonded with 2 oxygen. And then you have dinitrogen pentaoxide. So distributed yung dalawa, but between the 2 nitrogen is also again another oxide. So one nitrogen is holding 2 and 1 half, or 1 electron actually. Okay, nitrogen acids and ions. The most popular here, of course, is the nitric acid. It is produced by the Oswald process. It is a strong oxidizing agent, and then another is the nitrous acid. But generally, the nitric acid is more popular than that of nitrous acid. When you will be working in the laboratory, please be careful with nitric acid because nitric acid with protein or your skin will form an orange layer. These are structures of nitric and nitrous acid showing the nitrate ions. And then these are the oxides of phosphorus. And this is the repeating diphosphate ions and polyphosphate ions. So this is a polyphosphate ion forming the PO sorry POP structure. So HPO4 plus HPO4 means removing one hydrogen here and one hydrogen there to form water, but binding together one oxygen. So, nung na-remove ito, OH, at kinuha yung H doon, had formed water. But the remaining oxygen is shared back. Nandito na siya, no? By the phosphorus. So, ganun din ang mangyayari dito. Another like that, or another like this, sorry, dito, in order to form again another HPO3 bonding with oxygen. So, ito is just simply a repeating ganito. Okay, that is